As described above, based on scheduler decision, the eNodeB send the data over air interface on PDSCH. Then, the UE receive the data and verifies the checksum and send to eNodeB and HARQ or NACK on PUCCH and PUSCH channels. The reported CQI is an estimation and errors can still occur on the transmission. It may be necessary to retransmit a packet that could not be decoded successfully by the UE. LTE provides two retransmission mechanisms, hybrid ARQ, HARQ, implemented on the physical layer for fast recovery from errors. Automatic repeat request, ARQ, is a NACK-based implemented on the RLC layer, invoked only if the HARQ fails. If neither HARQ or ARQ can recover a lost or corrupted packet, then the application layer is responsible for retransmitting the packet. The HARQ process for downlink transmission has the following characteristics. ACK-NACK feedback. The UE sends ACK and NACK feedback indications exactly 4 subframes after a transmission is received to inform the eNodeB whether retransmissions are required for a particular packet. Asynchronous HARQ. Even if ACK and NACK are sent at a fixed interval, the HARQ retransmission may occur at any time, without a predefined schedule. The eNodeB must continuously monitor the channel in order to not miss any retransmissions. Adaptive transmission. The UE may change some or all of the transmission attributes used in each retransmission, due to changes in the radio conditions. 8 HARQ processes and buffers. The UE must be able to handle up to 8 separate transmissions at once, overlapping in time. After coding the transport block in the eNodeB coder, the output are the systematics bit, S, parities P1 and P2 that will be transmitted to the UE over the air interface. The eNodeB does not send all of the coded bits for a transport block at once. Instead, it sends each coded output stream separately and waits to see if the UE needs the remaining bits to successfully decode the packet. First, the eNodeB sends to UE over PDSCH the original data systematics bits, S, with the checksum for error detection. The UE receives the S bits and attempts to decode them. If the checksum matches there were no errors in the transmission over the air interface, then the UE feedback the eNodeB that no further information is required, by sending a HARQ ACK indication. By receiving the ACK feedback from UE, the eNodeB discards P1 and P2 bits. Otherwise, if the systematics bits S is received with errors, then the UE stores the S bits in HARQ buffer, and informs the eNodeB that the transmission has failed by sending a HARQ NACK to the eNodeB. The eNodeB sends the P1, the first set of the parity or error corrections bits, to the UE. The UE combines the P1 bits with the stored S bits and attempts to decode the packet again. If the data is decoded correctly, then the UE sends a HARQ ACK to the eNodeB, which discards the remaining P2 bits, since they are not needed. The HARQ buffer is cleared and the UE waits for the next packet transmission. Since it takes time for the UE to receive a transmission and send a feedback, the eNodeB must wait before any subsequent transmission are sent. If the UE receives a transmission in subframe N, it must attempt to decode the packet and respond with an ACK or NACK in subframe N+4, 4 milliseconds later. This fixed time interval allows the eNodeB to identify which transmission the ACK or NACK relates to without having to send additional information on the uplink. The eNodeB then has 4 more subframes, 4 milliseconds, to decide what will be sent in subframe N+8. Subframe N+8 may contain a continuation of the current packet, the start of a new packet, or nothing at all, depending on the eNodeB scheduler algorithm. In this example, the eNodeB begins to send packet A to the UE by sending the first set of coded bits SA over the PDSCH in subframe N. The UE stores the bits in HARQ process 1 and begins to decode them. While it is waiting for the UE's response, the eNodeB sends a new packet to the UE, transmitting bits SB in subframe N+1. The UE stores the bits in HARQ process 2 and begins to decode them. The UE successfully decodes SA and sends an ACK to the eNodeB in subframe N+4. The buffer for HARQ process 1 is emptied and is ready to receive a new packet. The checksum for SB does not match, so the UE sends a NACK to the eNodeB in subframe N+5. SB remains in the buffer to be combined with any other bit sent by the eNodeB. At subframe N+8 the eNodeB begins the transmission of a new packet sending coded bits SC to the UE, which stores them in the buffer for HARQ process 1 and decodes them. At subframe N+9 the eNodeB continues the transmission of packet B by sending coded bits P1B to the UE. The UE combines them with the SB bits already in the buffer and attempts to decode the packet again. Because of the timing requirements for HARQ, the UE may have to process up to 8 packets overlapping in time, which requires 8 separate HARQ processes and buffers. Although the timing for a HARQ ACK-NACK is fixed at 4 subframes, the eNodeB is not required to transmit its response, a new packet or a HARQ retransmission, exactly 4 subframes later, nor is it required to use the same transmission format. On the PDSCH, HARQ is an asynchronous process, and the UE must continuously check the PDSCH to determine when, how and where its packets are being sent. Huawei, eNodeB use asynchronous adaptive HARQ in the downlink. In this HARQ scheme, a UE sends HARQ feedback ITTIs after the initial downlink transmission. If the feedback is a NACK, the eNodeB retransmits the data at least KTTIs after receiving the NACK. In FDD, both I and K are equal to 4. In TDD, K is greater than or equal to 4, and I depends on the uplink-downlink configurations, subframe assignment configurations in the following table, and subframe numbers. The second table lists the minimum intervals, I plus K, between the initial transmission and retransmission. The intervals vary depending on uplink-downlink configurations.